and welcome to the next section, which is on the general concept behind gradient boosting. So we basically have one job to do here in this section, and this is really understand how the, well, I guess somewhat complicated general idea of gradient boosting really works. Okay, let's directly dive in. So we'll basically now start completely from scratch again and forget everything that we've discussed before for regarding ADA boosting. So, well, I guess we can keep the general idea in mind, and I guess it's somewhat helpful to compare how gradient boosting is constructed, compared to ADA boost. But for the general idea, let's pretend to forget everything about this, and let's really start from scratch, and let's consider how we could learn an additive model, which is constructed here again as this weighted average of some base learners, lowercase b, from some base learner hypothesis space, how we could do this in an optimal manner and in a risk minimal manner. So one approach would be to say, well, we already know how to do this. I mean, this is exactly why we studied empirical risk minimization. So we simply write down our empirical risk function. We plug in our parameterized model form here. So how is this parameterized? Well, it has all of these theta m's, no problem. And it also has all of these beta m's, again, further parameters, who cares? And we now just jointly optimize this and find, well, the best parameterization that minimizes risk the most. This is at least somewhat problematic for various reasons. So the first one is this parameter space that we now would have to optimize over will be quite high dimensional. So it will be at least d times m dimensional, if d would be the amount of parameters we need for each base learner, plus these plus m parameters, capital M parameters for these beta guys here. So I guess this might not be so bad, but if these guys here are, I don't know, 50 dimensional and we are boosting with 1000 components, we would have to optimize over 50k parameters. So this is high dimensional. This is definitely doable nowadays in deep learning. We often optimize over even worse parameter spaces, but it's at least a challenge, and maybe there are some ways to get around that. The other problem is that if the parameter space is not purely numerical, so imagine, for example, and this is a very popular and important example, that our base learners are trees. We would now have to grow m trees in parallel. So this is more or less a very complicated discrete optimization problem. Remember that we already had to kind of come up with a specific algorithm to grow an individual tree. And now we would have to grow m trees in parallel so they work optimally together. This is doable, but it's hard to do this efficiently, and it's at least a lot of extra effort that we would have to put into that. And the third reason is, if we do what we are going to do now, so stage-wise additive modeling or gradient boosting, this has a lot of nice properties that we can make further use of. So this kind of iterative, greedy construction of our gradient boosting model has a lot of nice aspects that we can exploit for regularization, that we can exploit for early stopping, and so on. So in any case, let's now try to do this in an easier, more greedy fashion, which is the general way out for these types of complex optimization problems. So if you can't optimize everything jointly in parallel at the same point in time, so construct it stage-wise, greedily, do it one component at a time, and then never change what you have selected in the iterations before. So in this case here, what we would do is we would add these additive components one by one to our ensemble, and keep the current ensemble fixed, and only try to find the next component that drives down loss or risk the most. And if you do this iteratively, this is called forward stage-wise additive modeling, and this is kind of a template algorithm that lies behind gradient boosting. The thing is that this is still not particularly easy, because we are not. It's doable, it's implementable, but it's a little bit harder, because we now have to find a B which is not risk minimal with respect to a given certain data set, but which is risk minimal if we add this to an already existing function f hat, Like I said, one could now directly try to solve this, make this a little bit more concrete, but give me a little bit of rope. I want to do this a little bit differently here for gradient boosting. As I've said, the template algorithm before for forward stage additive modeling, it's not really an algorithm. We have to make it a little bit more concrete, and you now have to give me even more rope and consider with me a somewhat weird approach, or an approach that might sound a little bit weird in the beginning, but which will give rise to a really, really nice algorithmic principle, a really nice general principle, in my opinion, for loss optimal machine learning. So, in order to attack this problem, we'll now do a short thought experiment where we will consider kind of a fantasy type of model, which would be completely non-parametric, completely flexible, and we would parameterize this in a way, our model F. So at the moment we are doing, forget about ensembling for the moment, just consider this kind of weird, super flexible model F here together with me. So we'll parameterize this in a way that each parameter directly encodes the output of our model F at each training data point. If these would be, I don't know, 10 points here in our training sample, each parameter would be exactly the output of our model F at that training point xi. Now, of course, this is somewhat stupid, right? We can immediately create a model which has loss or risk 0, and we just make these f's here, f of xi's, these outputs exactly equal to the observed labels. And also this model doesn't generalize at all. So it tells us what happens here at that point, but it doesn't tell us anything what happens here in between the training data points. I mean, this is why we need some kind of a function, right? And this is not a function, this is basically just a discrete vector. But again, give me some rope. We'll slowly convert this into something that's really insightful and useful. And in order to be able to work on this with gradient boosting, I will also, and gradient descent, I will also assume that my loss function L is differentiable. What I now want to do is I want to figure out a principle, how I can take such a function. At the moment it's a vector, but later on it's going to transform this into a complete generalizing function. So I want to figure out a principle so I can use gradient descent on top of that function, and not on top of its parameters, but really on top of the kind of the whole function, to nudge the function by gradient descent into a risk minimal direction, or you could also say closer towards my data points or closer towards my labels. That's my goal. That goal is exactly the fundamental underlying idea behind gradient boosting. Let's start. So we have our finite parameter here that encodes our f. So this is just some model outputs exactly at our training data points. And we now initialize this somehow. And I will mainly now study regression, because that's a lot easier to explain in the beginning, and we'll later see that we can generalize all of this to classification, to survival analysis, Poisson regression, and so on. And for regression, I will also often stick to the simple example of L2 loss. Again, gradient boosting is super nicely generalizable to basically arbitrary loss functions. So if we would use L2 for regression, we would also know how to initialize our model. We just initialize this in a loss optimal manner to a constant value. So for example, to the mean of all our observed y values, which is exactly what I did here. If this is our starting point, how can we now figure out how to kind of change this, assumed function that might connect these points here? So how can we nudge that into a direction so the function moves closer to the data? Well, one idea is to use gradient descent on this and to run gradient descent on the risk of the function. So we've done this before, but now we have these weird parameters, which are the outputs of a function. So if you would do this at many points, you can kind of, or we could say for each training data point, we want to figure out kind of a movement force, a movement direction, so that the function is moved into a risk minimal direction. So what I now could do, I don't know, formally, just because I think this might be some interesting direction, I could take a look at my empirical risk of my current function f. evaluated on my training data as usual. And I now can just formally, stubbornly, take the partial derivative with respect to one of my parameters. And each parameter is a model output at the ith training observation. And I put a minus in front of this because at the end I want to minimize risk. So I want to walk into the direction of the negative gradient, and I don't want to increase my risk by going into the direction of the positive gradient. So I can now formally simply do this. So this would mean taking the partial derivative of this loss sum here, and all of these terms in the sum here from 1 to n, they will all vanish because they're all independent of f of xi, except for the term which refers to the ith training sample. So the only thing that remains from the sum here, trivially, will be the partial derivative of my loss evaluated at the ith training data point when I take the partial derivative with respect to f of xi. So I can now also kind of generally define, this thing here I will now call the pseudo-residuals. I can either define this at the ith training data point, or I can just write down a general formula. I will always denote my pseudo-residuals with r tilde, so to kind of connect it to the residual, also by notation, and it's already connected by name to the residuals, and why that is, I will make clear in a few seconds. So if I wanted to define this on some arbitrary model output f, because that's the only thing that's kind of the input to the residual, this would be exactly this partial derivative here of my loss function with respect to the symbolic variable f inside of the loss function and loss definition. And of course, a minus in front of this to negate it. So if we would take a look at this abstract principle and, well, evaluate this with pen and paper for the L2 loss function, and usually you can easily, for each loss function, do a quick calculation with pen and paper. So for most of the known loss functions, this is really, this partial derivative is really simple to calculate. Try this out for a couple of examples. Some of them I will show here in the slides. And the first one would be normal L2 loss for regression. So I'm going to sneak in this 0.5 constant here in front of it to cancel out with the exponent of 2. And if I calculate this, which you can do in, 1 second with pen and paper, you can directly see that the resulting formula of the pseudo-residuals for L2 loss are simply exactly the normal residual. So what that tells us is something that's pretty intuitive and pretty unsurprising, and that is, if we have a bunch of training data and if we have some model that approximates these training data, at each training data point, what we would like to do is we would like to take that point here at our function and would like to move it into the direction of the residual. I mean, kind of optimally, what we would like to do is to go all of the way, right? And then we would be exactly at our, we would interpolate our training data point, and we'll probably also start to overfit. What is a little bit unclear is what happens here at these other points where we are not exactly at training data, but we are not there yet in the construction principle. So let's now combine this with our forward stage-wise additive modeling principle. So this template algorithm here. So as you can see in forward stage-wise additive modeling, we already, in each iteration, we are assuming we already have a partially constructed ensemble function available to us. How can we now distort this partially constructed ensemble function and move it towards the labels and reduce risk? Well, we will do exactly what we just discussed. We will take our pseudo-residual formula and calculate this negative gradient here, assuming that all of our current model outputs are generated through our partially constructed ensemble fm-1. So this is just the current ensemble. It creates some predictions, and at these predictions, we will now create this negative gradient here with respect to the outputs and collect them all in a vector. So basically nothing new has happened. I'm just now evaluating this formula at my predictions, this pseudo-residual formula at the predictions of my currently constructed ensemble. And I will denote this with r tilde for pseudo-residuals at the mth iteration and for the ith training data point. So if you forget about the I, you will have an n-dimensional vector of pseudo-residuals for the mth iterations. And if I wanted to change my partially constructed ensemble now into a direction through a gradient descent update on all of its outputs into a risk minimal direction, what I would simply do is I guess that's a typo here, I would add the, that's a typo, that should be, I would add the negative gradient to my current model outputs times some step length. So let's see how this looks like through a simple animation. So I've constructed, as often before, some kind of sinusoidal data cloud here. I'm starting with an initialized model where I'm simply using the mean of my y's, and I'm now computing here on the left-hand side I'm visualizing here the pseudo-residuals, and in order to show this a little bit better, I've only plotted the vector of pseudo-residuals here without the data points on the right-hand side, and I will now, for each data point, I will add 0.6 times pseudo-residuals to my model outputs and to create a new vector or imagined function that's now a little bit closer, in this case actually quite a lot closer, to my data cloud and to my labels. So I've done this here once, and I guess I'm doing this a second time. I would now again compute the pseudo-residuals at each point, which for L2-Lus would just be the residuals. I've visualized them here again on the right-hand side because my first update already reduced risk quite a lot. So the residual point cloud here is now a lot more centered around 0. And again, I would move 0.6 of these residuals now closer to my training data points. And yes, again, you might ask, what happens here at these points in between? I have no generalization capability. Why am I not just like going all of the way in one iteration and overfitting completely? At least having risk 0. So it still doesn't really make sense. But we are now really, really, really close, wrapping this up and creating something that works. And the only component that's missing now is that, well, of course, we are not going to parameterize our model through an n-dimensional vector of outputs. What we will do instead is we will take a class of base learners, some simple functions. In each iteration, we will compute this pseudo-residual vector, but we will not add it to some model outputs because we're not parameterizing our model like that. What we will do is that we are going to say now that in order to pick the best base learner from our base learner space, what we should do is we should fit our base learner to this pseudo-residual vector, because if we now add this base learner to our currently partially constructed ensemble, it would be quite great if this base learner here is very, very close in its outputs to the vector of pseudo-residuals, because then if I add it to my function, I will nudge my partially constructed ensemble into this risk minimal direction. So the closer we are to these pseudo-residuals in each iteration, the closer we can make our B to these pseudo-residuals. Now, the happier we are, the more we will drive risk down if we add B to our ensemble. So what we can say is that B should correspond as closely as possible to this negative risk gradient, and this B will also now generalize over our complete function space. And if we're adding only B's to our ensemble, our complete F will of course then at the end be a proper function that we can evaluate at each point in our input space. So again, because this is pretty complicated, I have slowly visualized this here in animation. We take exactly the same data as before. As before, we just initialized this with a constant mean function. We would now, interpret the mean really as a constant function that we can evaluate at each point. I guess that's hopefully clear that this is possible. And we will now see that how boosting works. Let's start with the nutshell definition. So one boosting iteration is exactly one approximated gradient descent step in function space, which minimizes the empirical risk as much as possible. So what are we going to do operationally? For our given current function, we will compute the vector of pseudo-residuals, which is visualized again here on the right-hand side. And these are the corresponding true residuals. And in this case, for L2 risk, for the L2 loss, they coincide, they are the same. So each point here, the y coordinate of each point is exactly the length of the arrow here on the left-hand side of the residual arrow. And to this vector of pseudo-residuals, I will now fit my base learner. So in this case, potentially some simple spline function. Yeah? And this will approximate this vector here. It won't be perfect. It won't represent the vector of pseudo-residuals perfectly at each training data point, but it's a complete proper function. And I will now add this to my current ensemble, which is just this simple stupid mean function here, which would result in this yellow guy here. So we're going from the ensemble at iteration 0 by adding this base learner here, which approximates the vector of pseudo-residuals. So by adding this to F0, we go to F1. We have now one component in ensemble if we don't count the intercept, this mean initialization. And we now can do this a second time. We usually use this learning rate principle, so we don't add the complete function, but we add some fraction of the function. So we would usually downscale this a little bit by, I'm not sure what I did here, probably I'm adding, using a learning rate as defined as 0.6 as before. Do the same thing in the second iteration. Again, you can see that the vector of pseudo-residuals here is more centered around 0, so it kind of globally goes down a bit. And I do this again and again and again. I guess I'm using a learning rate of 0.4 here. And I do this again and again and again. And you can really see how this function is nudged more and more closer to our data. And we can really define the direction of this nudging so it is optimal with respect to the given loss function. And because this is, because our vector of pseudo-residuals is directly defined for a given specific loss function. Here's the algorithm summarized in pseudocode. I probably don't have to say too much about this as we have covered all of the individual steps before. So let me go over this quite quickly. So we would initialize our intercept. So we just find the constant that's loss optimal for a given loss function. We've discussed at length in this lecture how to do this for loss functions. And if you don't know how to do this analytically, you can always use simple numerical optimization to find the initializing intercept for a given loss function. And now we do m iterations for boosting. So that's a major tuning constant, how many iterations we should do. And in each iteration, we compute our vector of pseudo-residuals, evaluate it for our current existing ensemble. We fit a regression base learner to the pseudo-residuals from our base learner space. By solving this risk minimization principle. And here we will usually always use L2 loss. So this is not going to use our input loss function, but this will simply use L2 loss. So to kind of use some simple, efficient, fast principle that's usually compatible with every type of base learner here in order to approximate our vector of pseudo-residuals. So if you want to implement that, you would take your original data matrix and you would swap out the y column to this calculated vector of pseudo-residuals, fit against that through L2 loss. And usually you can do this very, very fast for any given class of base learners. And now we somehow pick a learning rate. So I'm going to add a few comments on how to do that later on. So for now, assume just using a small constant. This small constant times the fitted base learner gives us the additive change we have to make to our current ensemble. And at the end, after m iterations, we simply stop and return this guy here. As I said, some comments about the learning rate. So as always, this also influences how fast we converge or whether we potentially overstep some local minimum. As the number of iterations in boosting, this is also an important tuning constant. There are a couple of ways how to deal with this in the direct implementation of the algorithm. So one way is, the most simple way and the most naive way. It's still very often used in many implementations, and that is just using some small constant and maybe to tune this offline later on. What we could also do is we could run a line search. So after this B hat guy here is fixed, we could also ask ourselves, well, if we look at this ensemble here, which is only parameterized by the learning rate beta, what is the best beta so loss becomes minimal? This would This defines a univariate optimization problem, which is not difficult to solve. So you can either run something like an exact line search algorithm on that, which would require some computation time. Maybe we are not okay with spending that, and some intermediate technique, some trade-off technique, which is maybe a bit better than using a fixed constant for all iterations. Could also be an inexact backtracking line search where we try out a pretty large learning rate and then we, I don't know, half it. If this doesn't drive down risk, or doesn't drive down risk enough, we halve the learning rate, we halve the step length, try it out again. If this drives down risk enough, we take it and stop, or we halve it again, we halve it again, we halve it again. And usually, you can kind of see that this is kind of this is probably going to invest something like a logarithmic number of steps in the end. Usually we are going to stop quite early after a few trial steps, and this is called backtracking line search, and often also combined with gradient descent in general numerical optimization.